It's not there.
Yeah. So this is a new one.
You're a big guy.
Yeah.
Well, it seems like it's an orchestage. No. Which way is it? I've got.
Is that too high? Oh, good. Okay.
Oh, yeah, but I don't ever use that way anymore.
Hi, how are you?
I have one. I bring it over my car. This one, I mean, finger right next to my Mac is turned off.
You know, I work at John.
This one, not so much rush, so like right next to it.
Well, I think you can do that for yourself. And then I can have them up back there. I'm going to keep my hair from your face. Oh my God.
Yeah, it's a late,
So how did you advertise this?
Well, we let the student really
I am probably
Does he
here.
know all of the various parts?
he probably doesn't.
I'm
Yeah.
Well,
I
I saw the announcement in Faraday, but I was at the community breakfast this morning, and then I understood more about it. So, but they could be ever, the Geneseo Sun, which is the online paper,
Yep.
they could be interviewed by that, and then in a letter, I mean, not a letter, an article.
Are you still reading books?
We did do a press release and they picked it up this morning.
Yeah.
Showed up in there.
And we're members of the Friends of the Library, which we did not receive one from them. And it's not one of their owners,
Right.
but they should be interested in
Right.
supporting
Right.
Chicago.
It's a road.
And
Supposed to be a very
I did have them added to the Geneseo and why
I'm gonna do a test.
after Thursday's meeting.
I'm good. I can learn.
So that would begin to help, and maybe a little bit more explanation as to what it actually is.
Well,
I got the
I
email
wasn't a
from
little kid,
the new.
All right, everyone, we're going to get started
chairman
in
of
just a
the
minute.
chemistry-
I just wanted to really quickly introduce myself. My name is Patrick Buckley. I'm a junior biochemistry student at Geneseo. I'm really excited to have you all here, so thank you all so much for coming. This is obviously the Discovery Cafe. I just wanted to start off with our mission statement, kind of make it like a little tradition for us. So the Discovery Cafe supports the betterment of society by using trust-building events to facilitate mutually engaging connections between scientists, researchers, and Western New Yorkers. So really, we're just wanting a really casual event for you guys to have some fun here. Please give us your feedback at the end. We'll definitely have surveys for you. So right now, I want to introduce Dr. Kirk Fletcher. He's a SUNY Distinguished Teaching Professor of Physics and Astronomy. He has a PhD in nuclear physics from the University of North Carolina. And of course, he's a teaching professor at SUNY Geneseo. I've actually had a class with him. So, I also wanted to really quickly thank the people in the room that have helped me get here. Of course, Dr. Fletcher. Dr. Bailey just walked in. He's my research advisor. Dr. Parfit has done a ton of work with the Institute for Community Wellbeing. Dr. Cope from the CIDD has provided countless support to me, so I can't thank them enough. And of course, Drizel is volunteering for me in the back. So, also, really quickly, I just want to thank the entire College of SUNY Geneseo for supporting this. The Center for Inquiry, Discovery, and Development, as I mentioned before, the CIDD. I'm supported by the James Houston Class of 1980 Ambassadorship in Innovation, which provided funds for this event and countless support mechanisms, so I really can't thank the college enough for this. Before we start, I just want to encourage you all to ask any questions. Just raise your hand. This is an event for you guys, so we don't want you to leave here with any questions, and we'll also have an opportunity at the end to have one-on-one questions with Dr. Fletcher. So with that, I'll turn it over to Dr. Fletcher, but thank you all so much for coming.
Thank you, Patrick. How's everybody doing today? That's exactly what happens in my class. How's everybody doing today? Fantastic. I'm wonderful. Thank you. Patrick asked me if I wanted to get involved in this, and he said that I could talk to people about physics. I like talking, I like people, and I like physics. So all of that is a great thing. I sometimes joke when I do some of these public demo shows that if you come here because you have a deep intellectual curiosity and you're hoping to learn about some of the great mysteries of nature, you might be slightly disappointed because I'm not going to delve too deeply into many things. But hopefully I will show you a few things that you may not have seen before. We called this a series of discrepant events, and I'm hoping that some of these things will be things that you will be a little bit surprised about, and maybe will help you appreciate the fact that, or the thing that I like the most about physics, which is when I get surprised and when I realize that my common sense doesn't work at all, and that nature behaves the way that nature behaves, and that's the way it is. So I have a bunch of demos here today. I teach with demos in my classes, not every day, but I try to do demos whenever I can to make points with my students. And so I brought some of them today, and we're going to do some of these demos and then talk a little bit about the physics around it. And the first thing I guess we'll do is, I think we'll start with this thing. I brought my gorgeous stepladder from my house. By the way, just for the record, I live 4 houses down from here. I live on 2nd Street. I live in Geneseo. I've been here at the college since 1993. My kids graduated from Geneseo Central, and my youngest son just graduated in May from SUNY Geneseo. And I grew up in Western New York. I grew up in Chautauqua County, in Frewsburg, New York. Woo! Nobody cheers. Okay. Home of the Frewsburg Bears. But anyway, so when Patrick was saying, that this is for Western New Yorkers, I feel pretty Western New Yorky about everything in my life. I married a Western New York girl. So what do we have here? This is a device that allows us to do a little demo. And one thing I like especially about this device is that one of my physics majors and his dad designed this one summer. One of my students Sam was working on an internship at the Science Museum of Long Island, and they asked him to come up with the demo. And he and his dad built a version of this in their garage. And he brought it to campus and showed me, and I said, well, that's great. And so my students and I have built about a dozen of these things, and we're going to be going to local high school classrooms, local physics classrooms, and using this demo there. So what are we going to do here? Well, I've got 2 different spheres, and should have thought about that beforehand. Okay, I've got 2 different spheres, and I'm going to put a sphere on either end of this thing. There's a rod that's going through there, and I'm trying to make this more or less level. Does it seem level to you? Okay. And so what does this do? Well, I can put a ball on this side, and I can put a ball on this little shelf here. And when I release this, actually I'm going to remove this one. When I release this, the spring will fire the ball, and it'll go off to the side. Like that. Very exciting.
Wow.
And if I release it this way, when I release it this way, this ball is not going to go off to the side. This ball is going to simply drop. Okay? So it's designed so that I can do both of those things at once. Thank you very much. And so the question that I pose to my students is, what's going to happen here? Which of these is going to hit the ground first? That's the question that we ask. Okay, so the spring breaks. No, it didn't break. That's the other thing. The wonderful thing about physics demos is that they generally go wrong. Something goes horribly wrong. I didn't bring any flammable stuff today. So I've got this set up here. So the one ball, of course, is just going to fall straight down. So clearly, it's traveling a much shorter distance than the launched ball. So we have a dropped ball and a launched ball. The launched ball is going to be launched. It's going to end up over there. And so the question that we ask is, what's going to happen? Which one's going to hit the ground first, the drop ball or the launch ball? So think about that for a minute. And how many of you say that the drop ball is going to hit the ground first? Nobody wants to say that, because I set that up that way, because I tried to convince you. Now you don't trust me, thanks. Okay. How many people think that the launch ball is going to hit the ground first? Okay. How many people think that it's none of the above? Okay. So let's find out. Okay. This is a very sophisticated audience here. Here we go. Ready? And if you've heard it, they hit at the same time. Okay. And the reason that this is an interesting demo, thank you, is because it illustrates something that we talked about in our introductory physics classes about how the motion of the ball in the horizontal direction is completely independent of the motion of the ball in the vertical direction. So both balls are falling from the same height. So they're going to fall at the same rate. It takes them the same amount of time to get to the ground. But the launch ball also has some horizontal velocity, which pushes it to the side. Doesn't matter. It's not going to affect how long it takes for the ball to reach the ground. Let's try it again, and listen for the sounds. And they hit. Now, when I did this demo, I actually did this demo on Saturday for Family Weekend. And when I did this demo on Family Weekend, I got about a third, and a third of people voting for which one was going to do what. So there's an example of that. Let me look at. Let's try another discrepant event, perhaps. Here I have two tracks. Yes. Okay.
If the balls were not the same,
Mhm.
it would be different.
It would sort of, well, that is a wonderful question. Because I ask you then, how are they not the same?
Wait,
Okay. If they're different weights, then they still are going to fall at the same rate. But if they are made, what we're talking about, that's what you just asked. Actually, now I'm going to go off for about 45 minutes. So, thanks a lot. If, let's suppose one was like a Nerf ball and one was the wood ball, right? This business that I just said was a complete lie. I told you that the vertical motion and the horizontal motion are independent and that they will both hit the ground at the same time. That assumed something which I didn't say, which was air resistance. I assumed there was no air resistance. I assumed that in a vacuum, for example, these things would fall at the same rate, right? And it is certainly true that if we had a Nerf ball and we had a golf ball, they would go off, they would fall at different rates only because of the effect of air resistance. And what I tell my students in introductory physics is this. We start out with telling them things that aren't true. And we tell them things that are truer and truer as time goes by. So if you're a freshman physics major, you ignore air resistance, right? If you're taking classical mechanics as a junior physics major, then you start to include air resistance into your calculations. And so you're getting something that's a little bit closer to nature. And if you take a graduate course, you add some more things. You might add the fact that the balls could be spinning. That might affect the motion of the balls. Or they have a different rotational inertia, or whatever it is. we can get closer, we try to get closer and closer to what's actually happening in nature, but in order, because we want to teach physics to people when at the same time that they're taking Calculus 1, we have to choose the problems that we do and the questions that we ask in a way so that they can solve them. And so we limit the things that we're talking about. So that was a really deep question. Thank you. Any other questions? Yeah.
Is the velocity of the ball that has more horizontal distance and traveling faster?
That's also an interesting question. It's a good question. Both of the balls have the same, again, in the absence of air resistance, both of the balls have the same vertical speed. But this one has no horizontal speed, right? This one has a horizontal speed. So we would use, in our physics class, we would use the language of vectors, and we would say that this velocity has components, horizontal components and vertical components of velocity. And yes, this ball will have a greater speed because it has a horizontal component, but its vertical components are the same. Yeah. Let me go with the back row first and then, yeah.
So if you pull the rod out farther and give the objective ball more velocity, will it still be the same because the distance between that the rod has to slip through the ball and that was the same, is longer? Does that make sense?
I can give it more, I think so. I think what you're asking is, like, I
Will it stay
can,
the same if you add more velocity to the...
yeah, so I can launch it just a little bit, or I could really give it a lot of impact there. That was,
But if you're like really back, they still
Yeah.
about the same.
they should, yes. Assuming, so that's actually a great question too, because that's assuming that they launch it at the same time. So if this ball has to slide, it depends on how long this one takes, right? If this one is sliding, it's staying in one place for a long time, and it could be, if this were longer, it could be that this one was launching earlier, right?
Yeah.
So in that sense, it could be different, but not in another sense. What was your question?
Now, if they were a little smaller, would the same reaction, would the reduction be the same or no?
Yes. And as a matter of fact, I have another demo set up which is smaller. I have ones with balls that are maybe a third of this diameter, and you see the same effect. And when I did this demo, over the weekend for people, I did it in I did it in Newton 204, and I actually had a much higher ladder, right? So they end up in the air longer, and you still got the same result. Okay. Great, thank you. Now I'm trying to do this, so I'm very proud of the fact that I drilled holes in all these balls so that you could not lose them. Okay, so now we have, let me go to this second demo here. I have 2 tracks, and now we need Patrick. Patrick is going to be doing the death-defying thing of catching the spheres. So, and this is another demo that we made, although it's inspired by things that other people have done. So I have a track, I can release this ball, and the track is just a V-shaped track. The ball is going to slide down here. It goes uphill first, then it goes downhill, and then it ends up in the cup. So that's what the first ball does. Okay. And then I have another ball over here, and another track, and this track goes downhill first, and then goes uphill, and ends up in the cup. Okay. So the question for you is, which one is going to win? We call this the race. Will the ball that goes uphill first and then downhill, will it get to the cup first? Or will the ball that goes downhill first and then uphill win? Or will they tie? Okay. So how many people, and in class, I actually, because we're very high tech, I have a cell phone system where students can respond to questions. So, and we can look at a bar graph on the screen that tells us what people, what the bolts are like. But, so let's say, how many people think that the ball that goes uphill first is going to win the race? Okay, well, thank you. 3 people. Downhill first win the race. How many people think it's going to be a tie? Oh, so the tie is the big winner here, right? And I'm going to help Keith out. The tie is the big winner. So, and why did you folks say, let me just ask, why did you think it was a tie? Yeah. Because we took the same bars, they're the same length, we bent them a little bit differently, but they're equal distance. Okay, that's a good reasoning. What else might lead you to think there's a tie? Yeah.
They end at the same space.
They end at the same space, and so you think that they're just going to reach that same space again? Okay, let's try it. So now, when we were rehearsing this earlier, this ball kept jumping the track because the track was dense, and I'm hoping it won't do it again, but now it's going to work good. You can hold it a little bit further away just so that the balls don't bounce off. Okay, ready? So here we go. So what happened? The down one went first, right? The downhill one went first. Let's try. Let's just make sure that that happens more than once. Okay, here we go. Yeah, downhill one goes first. Now, why is that? Yeah. I'm sorry.
I learned this in tech class.
Okay.
I'm an eighth grader. Because first, the ball is going faster on the downhill track, and then as it goes up, the ball that is going on the uphill track is slowing down when it goes back up. So the downhill ones will be going there first.
That's a very nice explanation. And when I explain this to people, what I say, and by the way, the first time I saw this demo, which is actually like 10 years ago or 12 years ago, I got it wrong. I got it completely wrong. And that's because I know too much physics and not enough. Because I thought, I was thinking like a physicist. I said, hey, they have the same gravitational potential energy. And I know about energy conservation. And I know that that means that as long as no energy is dissipated, that they should end up with the same kinetic energy, because they're at the same height at the end, right? So the change in their gravitational potential energy should become their kinetic energy at the end, and they would have the same kinetic energy, and so therefore they should tie, right? But that doesn't take into, and it's true actually, that this ball is moving this ball has the same momentum as this one does when it gets to the cup. They have the same velocity. What's different, but that doesn't tell you anything about time, okay? When the balls are tied here, this one speeds up. So when it travels, I think of this as a little flat distance. When it travels a little flat distance, it's going faster than this one is going to do when it travels a little flat distance. So it gets ahead, and the other one can never catch up. If we were doing this like again in the junior level classical mechanics course, we would integrate up to find that we'd have to do an integral to do the time. But and I'll answer your question. I'm going to do it one more time because I just like. You're first. Yeah. Eddie,
You answered it. Is there a way to calibrate where it would end up in a tie based on where you put the ball?
Oh, that's a great question. So you're saying like if I were to do it like this, could I get them to tie? If I
is there a formula to
like
calibrate?
this.
Calibrate.
Yeah, I think yes, one could do that. Well, I don't know. It's not going to go as they go. And if this were longer, I could do something like that, but I don't think I can with the way that's. What was your question?
If the tracks were double the length and reversed, so if you just coupled the tracks, would you get a difference?
Oh my gosh. Oh, I'm getting a headache. I don't know the answer to that. So you're saying if I took another track and had it go uphill and this one go downhill and so on. Well, since yeah, I think they would tie. But I could be completely wrong, and that's why it's great. Now I'm going to have to build one of them. that's the other kind of cool thing about science is that whenever we don't know the answer to things, we can do experiments and find out, nobody can argue with nature, right? And so if you're doing other fields of human endeavors, sometimes people can have passionate debates about whether one thing's true or another thing's true. In science, we we do experiments, and if we do enough experiments and we do them correctly, then we get the answers. We know what the answers are. So that's kind of the neat. Other questions about the
Would it be true that if you extended both of those longer, that farther ball would still get the same section until, of course, friction stops it?
It would still be ahead. Is that what you're asking? Yeah. Okay. Good. How are we doing? We're doing really fantastic. So I guess then the plan here, by the way, is I'm going to do about another 10-15 minutes of like presenting like this. Then we can do some more question and answer. And I have some smaller demos over here that people can look at on the table, and I'll be over by the table to do this. But so this is like our little finale of the big demo stuff. And this is called a Van de Graaff generator. How many people have seen a Van de Graaff generator before? So many people have seen it. So you don't want me to do it. Okay. Let me say a little bit about what this thing is. Down here inside this box, is this blue? I'm colorblind. Okay. Inside this blue box, I do this with my students all the time. I'm partially colorblind, and I might think that this is purple, so that's why I asked. But there is a motor, and the motor is connected to a wooden rod. You can actually, if you want to come up here and look, you can sort of see it. And it just spins. So there's like a little cylinder which is spinning really fast. And then there's a continuous, basically like a giant rubber band. It's made out of the same kind of material that balloons are made out of. But it's just a band here. At the bottom here, the rubber band actually is kind of just barely touching or very close to some wire mesh. And you can see in the top the same thing. You can see the wire mesh there on the side. Okay, thank you. I brought the good one. There's another one which is like 40 years old. So there's a wire mesh in the bottom like this. Now, everybody probably has an uncle or somebody who at birthday parties takes balloons and rubs them on their sweater, and then it sticks, or the hair. You're generating static electricity, and you're transferring electrical charge from one service to another service. That's what happens in static electricity. The same thing is happening here. This is basically like just a continuous way to rub that charge. So we're taking some charge. Actually, we're removing some charge from some negative charges, some electrons from the belt, and this wire mesh is at the top is connected to this metal sphere. And so what happens is the end result of this, when I turn it on, is that the sphere becomes positively charged. So we end up with positive charges. And I guess we have to show it. Okay, so it's on. How far away are you? Okay. And also, this is a bad demo to do today because it's humid. And electrostatic demos are awful when it's humid. Okay. Patrick, can you hit those lights that are by the fire extinguisher? Note where the fire extinguisher is. Okay. So we're making electrical charges here. The thing is getting the sphere is getting charged up positively, and then this is grounded, and so the charge can move to this sphere that we have here and travel through the wire and dissipate to the ground. When I touch it, then I don't get hurt when I turn it off. So that's charging up the Van de Graaff generator. So then there's a bunch of things you can do with Van de Graaff generators, and at science museums they have people stand on very good insulators and put their hands on these things, and then their hair sticks up. And we don't do that, so instead we have pieces of paper. This is just paper. Right? This is just paper which is attached to a frisbee, and so it's sticking out here. Again, I can I can attract the charges with the grounded sphere here like that. So that's all pretty cool. So that's fun. But that's not the demo I wanted to show you.
I have a question.
Yes.
Does that mean each one of the papers now has a positive charge and so they repel each other a little
Yeah.
bit too, and that's what makes
Yeah.
them stick up?
Yeah, well, yes. I mean, paper is not a conductor, so I'm not, the way that it gets charged up is a little bit different, but I haven't tried this demo, but everybody tells me I should do it. Let's try it. This is actually literally the first time I've tried it. There's 2 aluminum cans here. I think that it'll fly off, but I'm not sure. Yeah. There we go. Whoa! So they got charged up, and so then they, wait, did you get a shock? No. So they got charged up, and then they actually discharged, or they actually pushed each other away because like charges repel. Okay, so 2 kinds of electrical charges, of course. There's positive charges and there's negative charges. And what did Paula Abdul teach us? Thank you. Nobody who's 20 years old gets that. Okay? I have this whole classroom of people, and I do the Paula Abdul thing, and they don't know about the video with the cat or anything. Opposite charges attract, and like charges repel, of course. And so that's great. So what I'm going to do now is I'm going to do this Van de Graaff demo. I brought some. Let's actually turn the lights back. I brought some bubbles in here. Oh, that's going to work nicely. So there's a whole bunch of bubbles. Okay. Now what I'm going to do is I'm actually going to turn on the Van de Graaff generator, and then I'm going to blow a bunch of bubbles like that. And my question to you is, what is going to happen to the bubbles? Okay. Take a minute and talk to your neighbors. Have a little slight discussion. What do you think is going to happen to the bubbles?
They won't even get close.
One possible answer could be absolutely nothing. Wouldn't that be great if I did a demo that nothing happened? You can't see her. Can I, if I do this, is this better? Sooner or later they will pop. Okay. So what do we? It's whatever. It's whatever. This is authentic Walmart bubble stuff. There's nothing fancy about it. I bought it. Actually, probably 2 years ago, but I bought it at Walmart. It's regular old bubble soap. There's nothing special about it. Who has a prediction? What's your prediction? So you're saying that these bubbles are going to get attracted to the sphere. Now, why would they do that? Why do you say that? How is it that if they had a neutral charge that they would end up being attracted?
Still be less positive charge instead of electricity.
You are doing great. Okay, here is the Van de Graaff generator. It is positively charged. Okay. Okay. Yeah. What do you think? What's your prediction? So she thinks they're going to go towards it, and you think they're going to go away from it. Okay, let's have a vote. How many people? This is a democracy. How many people think that it's going to go? That the bubbles are going to be attracted to this sphere?
What charge is this? Positive or
This is
negative?
positive. The sphere is positive.
And the bubbles are?
The bubbles are neutral.
Inside and out. Because if it wasn't inside and out, the bubbles would just.
No, because that's positive, because the bubbles are neutral, there's still less positive in that than there is in the Van de Graaff, therefore it should be attractive.
So what does neutral mean, by the way?
There's an even amount of positive and
There's
negative.
even amounts of positive charges and negative charges. Every electron has a proton to balance it out, right? So if you were an electron and you were attracted to it, there'd be a proton that would be repelled by it, right? Okay. But we didn't do our vote. How many people think it's going to be attracted? How many people think it's going to be repelled?
They're gonna dump it.
Okay, okay. So I'm now going to show you what happens, and then we will explain it. Okay? And here's, well, no, I'm not going to ruin it. Okay? Okay, so watch very closely because it's hard to observe. Whoa, wait a sec. What just happened there?
The bigger ones work to it, the smaller ones went away from it.
You're both right. That's why I was so happy. You're both right. The bubbles are attracted to it, and then they're repelled by it. Did you see that? Okay, watch this again. Well, you can sort of see that. So, hang on just a sec. I'm trying not to get shocked. Okay. So what happened, and how does this happen? Well, what happened to the? Yes, this happens to the class. There we go. So a bubble, the bubble liquid is it's a liquid. So let's imagine here's a bubble. Okay. And now the bubble is a liquid, and the charges are in that surface of the bubble are free to move around. Okay, so the electrons, the negative charges, end up being attracted towards the Van de Graaff, and they leave behind some positively charged atoms on the other side. We say that the bubble is polarized. The charge is polarized. Okay. Now, this side, the side that's closest to the Van de Graaff, feels a force attracting it to the Van de Graaff. This feels a force which is repelling it. But because because these charges are further away, that force is smaller. So the overall result is that the bubbles get attracted to the Van de Graaff. Then a new thing happens. Because there's a bunch of bubbles here, right? There's several bubbles. The first bubble comes up to the Van de Graaff. Now, all these bubbles are neutral. They have equal numbers of positive and negative charges. The first bubble comes to the Van de Graaff, and it pops, and it splatters. It's touching the Van de Graaff. The liquid picks up positive charge and splatters, and little droplets of soap come over here and make these neutral bubbles positively charged. And so then they get pushed away. Isn't that amazing? Nobody would predict that, right? Isn't that amazing that happens that way? And you could see the surface of the Van de Graaff has some liquid on it now because the bubbles hit it. And so it wasn't working very well when I tried it at the end because I had to wipe it off. So now, because it was splattering off the soapy water, right? So now, you should see, now that you know the story, right, you should be able to see that the bubbles drift slowly. It's not literally a strong attraction. They drift slowly towards the Van de Graaff. And then when the first one, yes. That was me. When the first one hits, you'll see it splatter, you'll see that the other bubbles suddenly pick up charge and move away. Well, that's not going to work. It'd be nice if I knew how to blow bubbles. Okay. There you go. Okay. You could even see some of the bubbles were elongated, right? See how they stretch out? That's because they're polarized like that. They're feeling forces that are pulling them towards the Van de Graaff and pushing them away from the Van de Graaff. And there you go. This is one of my thank you. Thank you for protecting us from the bubbles and making sure they get all broken before. This is one of my favorite demos to do because of that. Because it's a complicated thing. It's not just one thing. It's a whole bunch of things. It's about the neutral bubbles becoming polarized and having charges moving to the side, and then the other bubbles becoming charged up because of the thing. And now I have this stuff over. questions?
So the bubbles moving away now have a full positive charge.
Yep. They have some positive charge. And so they feel, so they're, because opposite charges repel, I'm sorry, because like charges repel, they feel a force which pushes them up.
Where I was going, is the bubble going to shock me the same as?
No, it picks up a little bit of charge. That little splatter of charge, it's just a few, even just a few, a charge of just what we would call a few charges, a few electrons worth of charge is enough for the force to push it away, but it wouldn't really
Carry the charge.
It wouldn't. Okay. Yeah.
Is there a way to reverse that?
How so? What do you mean?
Like, if you had two Van de Graaffs on each side, would it just go up or down or whatever?
You guys ask fantastic questions. I've never imagined such a nefarious scheme. So you would have two Van de Graaffs charging, so then they both be positive.
Right.
And so that means bubbles here, I think, here's the answer to that, right? Why do the bubbles know about the charge at all? That's a great question. If you're a bubble sitting right here, how do you know that there's charges over there? Oh, everybody wants to, I'll go back here first. Why? What did you learn in tech class? Yeah.
Because the negatives in the bubble, when we flow to the positive, just like the opposites attract.
Great, and my question is, how do the negative charges in the bubble even know that there's positive charge over here? They can't see it, they don't have any eyes, they can't. Hmm?
My tech teacher has a lot of explaining to do.
Oh, okay.
Would the air around it also possibly harm?
It actually, well, today it might be because it's humid. And actually, I can feel like the hair on my arms when this is on, I can feel the charge here. But in empty space, again, if we were doing this without air around, you still would see the same thing. So in a perfect vacuum, if we were out in outer space, we would still, you still would have positive, a positive charge here would be repelled by this positive charge. But you were very close, yeah. So the bubble does this, and it feels, and those charges are on the drops, and they feel a force that pushes them away. And that force is kind of the whole thing, right? There's a man, a British physicist named Michael Faraday, who lived in the 1800s, who came up with, he was naturally taught. He was very poor and grew up poor and apprenticed himself to smart people, and he became, and he gained access to their libraries, and he taught himself a lot of science. And he wasn't very mathematical because he didn't have a college degree and things like that. So he came up with very qualitative ways of visualizing things. And one of the things that Michael Faraday came up with was what we call a field. So we imagine that the space around these objects actually is affected by the charges. And so the reason that a charge over here knows about a charge here is because of this mediating electric field, that there's something about the empty space, even without air in it, that is changed when we have positive charges here. And so you could draw, so I'm getting back to your, this is my long-winded way of getting back to your question about the double Van de Graaff. If I have two Van de Graeffs that are here, I can imagine the electric fields. So the electric fields are pushing, they would push positive charges outwards, right? They're always radially pointing outwards. And this one is also radially pointing outwards all the time. So in the middle, what happens is those field lines would go like this. And so yeah, I think the bubbles would sort of get pushed away. Well, when they got pushed away, they would get pushed away like that. If they were polarized, if they weren't charged, if they were neutral, then they still might get attracted to the one that they're closest to. Yeah, there's lots of cool stuff. Great. I think this is a good time to stop for now with this part of the thing. I have some things at the table we can talk about if you're interested. There's a whole platter of sandwiches if anybody wants that. What else should I tell them, Patrick?
I'm going to put you on the spot.
Okay.
Just really quick.
Sure.
Why does this all matter that we see all these unexpected?
Well, you know, because it's just beautiful. It's wonderful. Well, there's a bunch of answers to that question, and one answer is that we can use once we understand these kind of phenomena, we can use these phenomena to be able to do things that we want to do. So, for example, this Van de Graaff generator, this idea of having a belt that carries charge and this gets all charged up, physicists have actually taken this idea and turned it sideways like this, and have been able to create positively charged terminals here and build ion sources which make positively charged ions, and those positively charged ions are repelled by the positively charged terminal, and those ions go flying down the hall. This is called a Van de Graaff Accelerator. And we have in the basement of the Integrated Science Center at Geneseo, we have a particle accelerator which works basically on the same kind of process of charging up things. This is charging up to probably around 40,000 volts. The Van de Graaff we have goes up to 1.7 million volts. It's a big machine which is the size of a small bus. Not a bus. It's 12 feet long, let's just say that, okay? And so we can use those kinds of machines to accelerate charged ions and interact with targets. And I, by the way, am an experimental nuclear physicist. That's what my background is in. And that's one of the things that I do in my research is I accelerate subatomic particles that are positively charged, smash them into atoms, and then see what things are coming out of those atoms and study the reactions that occur. And so that's one application of some of the things. Great. Okay, so if you like, come on over and I'll show you a couple of small things. And I'm going to show this one first. Okay, so inside this box, can you see the blue globe, the blue track there? Okay. The track that you're seeing inside this evacuated tube is an electron beam. So what's happening is this tube is filled up with some, I think it's probably argon gas, but there's a little metal conical shaped object inside there which is an electron gun. It's shooting electrons out, and those electrons are bashing into the argon atoms and giving off light. The argon atoms are giving off light, and we're seeing the trail of those electrons as they pass through here, which I think is kind of cool. You can actually see the impact of electrons that are flying through this gas like this. Right? Now, around the outside of this tube is a electromagnet. This is a big coil, and if I turn on the electromagnet, and if I increase the magnetic field, what happens? I can make those electrons bend around into a circle. And for those of you who may remember a physics class at one time or another, these electrons are undergoing centripetal motion. They're actually going around in a circle. They feel a force which is constantly pushing them towards the center of the circle. And the magnetic field here inside this is actually pointing in this direction. So it's a weird thing. The electrons are going that way at the bottom. The the magnetic field is pointing inwards, and they feel a force that pushes them upwards. But that's the way that forces work on moving charges. The magnetic fields exert on moving charges. Patrick asked for applications before. So you may have heard of like cyclotrons. A cyclotron is a device which takes positive charges and moves them. They circle around for example, at CERN over many miles in a big, gigantic evacuated tube buried underground. How do those particles go around in a circle? Because of magnetic fields. And so they have electromagnets that generate magnetic fields. Also, in the early days, well, not everybody, some people will remember cathode ray tube televisions. And those were electron beams that were being fired at your screen, and they were being rastered. They were moving very fast to excite the phosphor on the screen. And magnetic fields and electric fields were used to push those electrons around. So that's kind of So, what they're doing is studying fundamental questions about these subatomic particles. And so there are models, there's theories that people have made about how these subatomic particles may interact with each other. We believe that we have what's called the standard model of particle physics, which is kind of the standard theory right now. We believe there's certain families of subatomic particles, and that there are 4 forces in the universe that control all of the forces that we see. There's gravitation, there is the weak nuclear force, the strong nuclear force, and the electromagnetic force. And so they're studying those forces and also studying the particles that are created in some of these reactions. And every once in a while, something brand new happens that doesn't match the model. And that's when things get exciting. Okay? So for up until 3 years ago or so, when I was teaching my modern physics kids, I would say that particles always, subatomic particles can be created from pairs of quarks or 3 quarks together, and that's all there is. And then somebody did an experiment at CERN and found a particle that was made out of 5 quarks. Nobody had predicted it wasn't part of the physics. So, there's a great story about, I think his name was Robert Wilson, was the first director of Fermilab, which is in Batavia, Illinois. It's a big accelerator laboratory. Has anybody been there? Yeah, okay. It's painted, you can see like the parts of it are painted blue and orange. Right? It's very cool. But when Congress was doing hearings on whether to fund Fermilab, Wilson was testifying in front of senators, and one of the senators asked Wilson, he said, well, this Fermilab that you're asking us to build, can you tell us how Fermilab will help with the defense of the United States? And Wilson thought for just a minute, he said, Senator, it will not have any impact on the defense of the United States, but it will make the United States worth defending. But if we have that, that's the way physicists sometimes think, but that was his response to that. Cool. I'll show you one other thing, I guess, and then if we want to play with it. This is just an aluminum rod, and I'm going to drop this thing through there. It's just a clear hole. So you wonder what's going on. Now, when I do this demo in class, I do something that's not really very nice. Yes, okay. Where did So let's try this here. So here we go. That one went really fast. But of course, I switched to the line, okay? So this one goes with this. So what's the difference? The one that's in the tube right now is actually a magnet. It's a bar magnet. Okay? Now this is made of aluminum, this tube. And so bar magnets do not stick to the aluminum. There's no, you take it and try to make it stick. Just a minute, right? And the inside of this is aluminum. It isn't that it gets stuck. What's really kind of fascinating is that when a magnetic field is moving like this, this moving magnetic field can actually cause charges to move around. It creates a current. It's Faraday's law. The moving magnetic field creates an electrical current. So the charges, the electrons in this aluminum start going around in a circle around this thing. And electrical currents create their own magnetic fields. So this creates a magnetic field which pushes against the field that's coming down. So it reaches a terminal velocity where the speed at which this is falling is such that it has a force downwards due to its weight, due to gravity. And it has a force upwards due to the magnetic field, which is equal and opposite. And then it just travels at a constant velocity. So.
Does this spiral?
But the cylinder itself doesn't spiral. The charges are moving around on the inside. Yeah. If you switch the bar magnet, it does the same thing. Well, that's the non-magnet. Yeah. So it doesn't matter which way the aluminum runs. This one has some Velcro on it because the company, the company that sells it sells a little packing and stickers on it. Yeah. There's a magnetic field pointing upwards. Yeah. If you could come up with another magnet that could counteract that magnetic field, I guess you could. I've never tried that. If you were to send a charge like a current this way, that wouldn't create a magnetic field which would be the right direction to push this away. So I don't think that would.
You got various different strengths.
Yes. Right, so, and I think what happens is that the terminal velocity is different depending on what's inside there. I actually have, now that you say that, I have another magnet. I haven't tried. Yeah, so that was a different
Oh, yes.
There's something. Okay, well, then if you like magnets, I'll show you one last thing. There's always a last thing. Okay, this is just Faraday's law. This is a coil of wire. It's actually 10,000 turns of wire that are wrapped around a piece of plastic. And this is a meter that tells you if electricity is flowing. So right now, you see the needle's at 0. Right, so if I take a magnet and I push a magnet into that wire, remember I said that a changing magnetic field will cause charges to flow. Right, and so. This is exactly how you generate electricity for your house. Okay, somewhere, whether it's a wind turbine or whether it's at Niagara Mohawk, somewhere something is causing magnets to move relative to coils of wires and is making charges. This is not the way you generate electricity if you're doing solar. Okay, but for most of the electricity that you would buy for your house, if it's hydroelectric or burning coal or something to heat up water, the water turbines churn something that makes magnets move relative. The simplest thing in the world, and it's just a purpose.
Alternating current
Yeah.
and AC, as opposed
to DC. So, and you can see it's alternating, this is, when it goes one way, it's negative, and one way so it's flowing through the wires different directions depending on that. And if I flip it over, it does the opposite. So if the north end of the magnet is pointing in, it'll do the opposite thing of what comes up. Good, thank you. I won't trap you here any longer, but if you have questions, come on over. Patrick, how can I go to another one of these Discovery Cafes in the future?
Well, October 4th, there's another event on personalized genomics in Perry, New York at 24th. Sorry, Tuesday, 24th, October 24th at Birmingham Books in Perry. And we have some flyers. We're also back here at Wadsworth Library on the 28th of November for the biology of extinct animals and dinosaurs. Also, real quick, while I have your attention, we really appreciate it if you felt this option survey. It would take like 2 minutes. It really helps us provide feedback so we can improve the event. If you like want certain foods, definitely tell us, certain things like that. It would also help us to understand if this is a useful event for everyone. So we really appreciate it if you fill it out. We have some surveys in the back right here with pens, and like I said, completely optional, but we really appreciate it. And thank you again all for coming. If you see on the schedule, we do have a question and answer session with Dr. Fletcher. So if you had any burning questions that you didn't want to ask with the whole group, please feel free. And thank you. Yes.
I'm not sure you want me to fill this out. You want me to fill it out? Okay.
Oh, Michael, real quick.
No,
No, with somebody else.